Mount St. Helens. At Mount St. Helens.
Mount St. Helens.
Mount St. Helens.
So when Mount St. Helens woke up in the spring of 1980, it was too good to be true. I could hardly believe that it was really happening.
Mount St. Helens has seen an increase in earthquake activity with nearly 350 quakes over the last several months.
Recent volcanic activity at Mount St. Helens has ignited not just curiosity, but deep concern. The fear is growing. Could this once devastating volcano trigger a chain reaction that awakens the sleeping giant Yellowstone supervolcano? These are two of the most powerful volcanic forces on Earth, each responsible for unimaginable destruction in the past. Imagine the catastrophe if they both erupted together. Could an eruption at Mount St. Helens really set off the deadly Yellowstone supervolcano with world-shattering consequences? It's a terrifying question that delves into the hidden forces of our planet. There's only one way to find out. Watch this video. Mount St. Helens, a volcanic giant. Mount St. Helens, located in Washington State, is part of the Cascade Range, a lineup of volcanoes that includes Mount Rainier, Mount Hood, and Mount Adams. However, Mount St. Helens stands out, not just for its striking cone shape, but for the violent eruptions that lie in its past. The world was forever changed on May 18, 1980. Mount St. Helens had been showing signs of activity for months: earthquakes, steam eruptions, and bulging of the north side. Yet no one could have predicted the sheer scale of destruction that was about to unfold. At 8:32 a.m., a magnitude 5.1 earthquake struck, triggering the largest landslide ever recorded. The entire north face of the volcano collapsed in a massive rock slide that roared down the mountain at speeds of up to 150 miles per hour. What followed was nothing short of apocalyptic. A lateral blast, a superheated cloud of gas, rock, and ash shot out of the side of the mountain at supersonic speeds, flattening everything in its path. Over 230 square miles of forest were obliterated in seconds. Glaciers melted, and a massive ash plume rose 15 miles into the atmosphere. Ash fell across 11 states and even reached parts of Canada. The once majestic peak of Mount St. Helens lost over 1,300 feet in height, leaving behind a gaping crater. This eruption wasn't just another volcanic event, it was a turning point in our understanding of volcanic power. Scientists around the world were stunned by the scale and ferocity of the explosion. In the aftermath, researchers scrambled to study the volcano, uncovering invaluable data about volcanic behavior. It became a natural laboratory for volcanologists to test their theories and refine their predictive models. This eruption reshaped how humanity perceives volcanic disasters. Before 1980, volcanologists had identified early warning signs of eruptions, but they had not yet fully understood how quickly a volcano could go from rumbling to a full-scale explosion. Mount St. Helens provided critical data on how magma movement beneath the surface can distort the landscape, a key indicator of future eruptions. Scientists learned to monitor ground deformation closely, adding this to their toolkit of predictive measures. In fact, modern volcanic monitoring systems owe a lot to the lessons learned during and after the 1980 disaster. Yet Mount St. Helens didn't simply go back to sleep after 1980. Over the years, the volcano has continued to show signs of life. Between 2004 and 2008, a series of smaller eruptions occurred, resulting in the gradual formation of new lava domes within the crater. These eruptions, while less dramatic than the 1980 event, remind us that Mount St. Helens is still very much active, and that another major eruption is not a matter of if, but when. But what makes Mount St. Helens so dangerous? To answer that, we need to take a closer look at the inner workings of this volcanic giant. Inside Mount St. Helens, understanding its volcanic mechanics. To fully grasp the potential danger posed by Mount St. Helens, we need to understand its structure and the processes that fuel its eruptions. Like many stratovolcanoes, Mount St. Helens is built from alternating layers of solidified lava flows, volcanic ash, and pumice. This gives the volcano its distinct cone shape, but it also reveals the complex volcanic history that lies beneath its slopes. Beneath the surface of Mount St. Helens lies a churning reservoir of molten rock known as magma. This magma is constantly moving and interacting with the Earth's crust. The buildup of pressure within this magma chamber is what ultimately leads to volcanic eruptions. But not all eruptions are the same. Some are relatively small, involving slow-moving lava flows, while others, like the 1980 eruption, are explosive and violent, sending superheated gas, ash, and rock into the sky. One of the most terrifying features of Mount St. Helens is its ability to produce pyroclastic flows. These deadly currents of hot gas, ash, and volcanic debris can travel at speeds of over 60 miles per hour and reach temperatures of up to 1,000 degrees Celsius. During the 1980 eruption, pyroclastic flows traveled over 17 miles, flattening forests and reshaping the landscape in the blink of an eye. These pyroclastic flows are dangerous for several reasons. First, their extreme speed and temperature make them nearly impossible to outrun or survive if caught in their path. Second, the massive amounts of ash and gas released into the atmosphere can disrupt global air travel, as ash clouds can cause severe damage to aircraft engines. This was seen in the 2010 geological eruption in Iceland, where airborne ash led to the largest air travel disruption since World War II. While Mount St. Helens's 1980 eruption predated this incident, it provided early lessons on how volcanic ash could affect modern aviation, a growing concern in today's interconnected world. Another major hazard posed by Mount St. Helens is the potential for large cars. Volcanic mudflows, triggered by the rapid melting of snow and glaciers during an eruption. In 1980, lahars flowed down the Toutle River, reaching the Columbia River over 50 miles away. These lahars carried massive amounts of debris, causing extensive damage to infrastructure and communities downstream. Future eruptions could trigger similar mudflows, posing a significant risk to the region. It's not just the immediate dangers of an eruption that concern scientists. The long-term effects on the landscape and ecosystem are equally profound. After the 1980 eruption, researchers documented the slow recovery of vegetation in the blast zone. The resilience of life was remarkable, but it also revealed just how fragile ecosystems are in the face of such destructive natural events. Even now, over 4 decades later, certain areas remain barren, while others have flourished as nature slowly reclaims the land. The landscape surrounding Mount St. Helens remains scarred by the events of 1980. The blast zone, extending over 230 square miles, is still visible today, though vegetation is slowly beginning to return. Spirit Lake, located northeast of the volcano, was dramatically altered by the landslide, its bed raised by 200 feet. The lake remains covered with floating logs, remnants of the forest that was destroyed in the eruption. Scientists continue to monitor Mount St. Helens closely. Each rumble, each plume of steam, and every minor eruption tells us that the volcano is still alive, and its next major eruption is inevitable. But could this eruption trigger something far worse? Could it set off a chain reaction that awakens other volcanoes in the Cascade Range, or even Yellowstone supervolcano? Volcanic triggering. Can one volcano awaken another? Volcanic triggering is the idea that activity at one volcano could potentially cause eruptions or seismic activity at nearby volcanoes. It's a concept that has fascinated scientists and the public alike. After all, the Cascade Range, where Mount St. Helens is located, is home to several other major volcanoes, including Mount Adams, Mount Hood, and Mount Rainier. Could an eruption at Mount St. Helens set off a chain reaction that affects these nearby volcanic systems? While volcanic triggering is a rare phenomenon, it's not impossible. Volcanoes in close proximity can be connected through shared magma chambers, tectonic stress, or seismic waves. When a large eruption occurs, it can redistribute stress in the Earth's crust, potentially influencing the behavior of nearby volcanoes. This is particularly true in regions like the Cascade Range, where multiple volcanoes are part of the same tectonic system. The science of volcanic triggering is complex. In some cases, nearby volcanic systems do interact. For example, in 2018, the Kilauea volcano in Hawaii triggered activity at the nearby Mauna Loa volcano, although it did not result in an eruption. However, these two volcanoes are part of the same volcanic complex, with interconnected magma systems and tectonic stress zones. In contrast, most volcanoes in the Cascade Range, while located relatively close to each other, do not share the same direct connections. In the case of Mount St. Helens, there is currently no direct evidence that it shares a magma chamber with other nearby volcanoes like Mount Adams or Mount Hood. While the 1980 eruption did increase seismic activity in the region, it did not trigger any major eruptions at other Cascade volcanoes. But what about Yellowstone? Could an eruption at Mount St. Helens travel over 500 miles and awaken the sleeping giant beneath Yellowstone National Park? This is where things get even more interesting. Mount St. Helens versus Yellowstone, two different monsters. Mount St. Helens and Yellowstone are two of the most powerful volcanic systems in the United States, but they are driven by entirely different geological processes. Understanding these differences is key to answering the question of whether one could trigger the other. Mount St. Helens, like the other volcanoes in the Cascade Range, is part of a subduction zone. This means that its eruptions are caused by the subduction of the Juan de Fuca plate beneath the North American plate. As the oceanic plate descends into the Earth, it melts and generates magma, which rises through the crust and fuels volcanic eruptions. This process leads to relatively frequent eruptions, though some, like the 1980 event, can be incredibly powerful. In contrast, Yellowstone supervolcano operates on a much larger scale and through a completely different mechanism. Yellowstone sits atop a mantle plume, a column of hot material that rises from deep within the Earth's mantle. This plume creates a hotspot where magma accumulates beneath the surface, leading to the formation of a massive magma chamber. While Mount St. Helens produces frequent, smaller eruptions, Yellowstone's eruptions are rare but catastrophic. The last major eruption at Yellowstone occurred over 640,000 years ago, and when it erupted, it created a caldera over 30 miles wide. The sheer volume of material released during a Yellowstone eruption is many times greater than anything Mount St. Helens could produce. In fact, a super eruption at Yellowstone would have global consequences, potentially disrupting climate, agriculture, and infrastructure around the world. The mantle plume that fuels Yellowstone is an entirely different kind of volcanic system than the one that fuels Mount St. Helens. This deep source of magma can't be disturbed by surface-level volcanic events hundreds of miles away. Yellowstone's magma chamber is much deeper and larger than Mount St. Helens. For Yellowstone to erupt, the pressure buildup in its own system would need to be enormous, and it would be unlikely that external forces, especially those from a volcano like Mount St. Helens, could trigger such an event. But could Mount St. Helens trigger Yellowstone? The short answer is no. Despite their proximity on the same continent, these two volcanic systems are not connected by shared magma sources or tectonic processes. Mount St. Helens is driven by subduction, while Yellowstone's activity is powered by a deep mantle plume. The forces that drive these two volcanoes are independent of each other. Hold on a second. If you're fascinated by the explosive story of Mount St. Helens and Yellowstone, make sure to hit that subscribe button and ring the notification bell to stay up to date with more thrilling deep dives into Earth's most powerful natural forces. Seismic waves and tectonic stress. Could there be a connection? While Mount St. Helens and Yellowstone are not connected by magma systems, some have speculated that the release of seismic energy during an eruption at Mount St. Helens could travel through the Earth's crust and impact Yellowstone. Seismic waves, after all, can travel long distances, and large eruptions often produce earthquakes that can be felt hundreds of miles away. It's true that the 1980 eruption of Mount St. Helens produced seismic waves that were felt in nearby states, but these waves did not have any measurable impact on Yellowstone. For an eruption at Yellowstone to occur, the conditions within its own magma chamber would need to change significantly. This process is driven by internal pressure buildup over long periods, and there is no evidence that external seismic waves from Mount St. Helens would be enough to trigger such a massive event. Similarly, the tectonic stress released during an eruption at Mount St. Helens would have little effect on Yellowstone. The two volcanoes are not part of the same fault system, and their tectonic environments are largely independent. Even within the Cascade Range, where volcanoes are much closer together, eruptions at one volcano rarely trigger eruptions at others. In fact, throughout history, there has been no recorded instance of volcanic activity at Mount St. Helens triggering an eruption at Yellowstone, or vice versa. The two systems are simply too far apart and too different in their geological processes. Could Yellowstone erupt in our lifetime? While Mount St. Helens and Yellowstone are not connected, the possibility of a future eruption at Yellowstone remains a topic of concern. Yellowstone is closely monitored by scientists who track ground deformation, gas emissions, and seismic activity. These indicators help researchers assess the likelihood of future eruptions. The good news is that while Yellowstone's supervolcano is capable of erupting again, the chances of it happening in our lifetime are extremely low. Super eruptions occur on timescales of hundreds of thousands of years, and there is no evidence to suggest that an eruption is imminent. However, scientists remain vigilant as Yellowstone's eruptions would have far-reaching consequences. For now, the greatest threat comes from smaller eruptions, like those at Mount St. Helens, which are more frequent but more localized in their impact. These eruptions, while dangerous, are manageable through careful monitoring and preparation. Two volcanoes, two separate threats. In the end, could Mount St. Helens trigger Yellowstone's supervolcano? The science says no. These two volcanic giants, while both dangerous, are driven by entirely different processes and are not connected in any meaningful way. Mount St. Helens operates within the subduction zone of the Cascade Range, while Yellowstone is fueled by a mantle plume deep within the Earth. While both pose significant risks, their threats are independent. Mount St. Helens will continue to be monitored for signs of increased activity, and another eruption is likely in the near future. Yellowstone, though a more distant threat, remains a topic of scientific interest and will continue to be studied for any signs of change. But for now, the next major eruption at Yellowstone is not likely to be triggered by Mount St. Helens or by any other volcano. Now, we'd love to hear from you. Which of these volcanic giants do you think poses the greatest risk to our world? Do you believe we're truly prepared for the next major eruption? Let us know your thoughts in the comments below. Thanks for watching. If you found this video informative, Be sure to subscribe for more insights into the incredible forces shaping our planet.